Hello everybody, this is VR Seshagiri Rao, Associate Professor in the Department of Electronics and Communication Engineering, Institute of Aeronautical Engineering College. Today I am going to discuss about the flag register of 8086 microprocessor. See, there are 14 general purpose registers. There are 14 registers in 8086. The registers are AX, BX, CX and DX. And in addition to these registers which are used for arithmetic and logic operations, we also have the segment registers, code segment register and extra segment register, stack segment register, data segment register, followed by the pointer registers which are used to store the offset address. They are instruction pointer, stack pointer, base pointer, source index and destination index. And other registers are flag register. So today I am going to discuss about the flag register. The flag register, it is a 16-bit register, and the various fields I am going to discuss about the flag register now. So it has 16 bits. This is the least significant bit and this is the most significant bit. The first four significant bits are not used. The first bit is the carry flag bit. It is used to store the information of carry flag. The next bit followed is not used. And after that we have the parity flag. And after parity flag, next bit is not used. And after parity flag, we have the auxiliary carry flag bit register. And after auxiliary carry flag, the next one is not used. Next is the 0 flag, which is followed by the sign flag. Then we have the T flag or the trap flag. Then the I flag, which is nothing but the interrupt flag. Then the direction flag, D flag. And lastly, we have the O flag, that is overflow flag. So this is the configuration of the flag register. Now we will examine the significance of these flags. So total we have 9 flags, and out of 9 flags, 3 are the control flags and 6 are the conditional flags. Now what are the 3 control flags? The direction flag, the interrupt flag and the trap flag. Now what is the direction flag? So this affects the direction of moving data blocks by such instructions like moves, CMPS and SCAS. And the flag values are 0 is up and 1 is down, and this can be activated or deactivated by STD or CLD instructions. See, in array processing, you can do the processing starting from the lowest element to the highest element or in reverse order. So if you are processing from the lowest element to the highest element, then direction flag is made as 0. Suppose you want to process the array starting from the highest address to the lowest address, then you have to keep the direction flag as 1. So this decides in which order you are processing the array. And this can be set or reset by using instructions setD or clearD instructions. SetD means you are making the direction flag as 1. ClearD means you are making the direction flag as 0. So if you are doing the ClearD instruction execution, then that means you are processing the array from the lowest address to the highest address. And if you are making the direction flag as 1 by using the set instruction, then you are processing the array in the reverse order. Next is the interrupt flag. So this decides whether or not the system can accept interrupts or not. What are the interrupts? Interrupts are the actions initiated by the hardware block, such as input devices, that will interrupt the normal execution of the program. So whenever any external devices need the service of the microprocessor, they send request signal. That request signal is called as the interrupt signal. So using this interrupt flag, you can mask or disable the interrupts. So if the interrupt flag is set, then that means the interrupts are enabled and the microprocessor can entertain the interrupts. And if the interrupts are disabled by using the instruction CLI, that means even if interrupts occur, the microprocessor is not going to recognize them. And again, the interrupts can be enabled by using the instruction STI. What is STI? STI is set interrupt. And CLI means clear interrupt. So set interrupt makes the interrupt flag as 1. And CLI, clear interrupt flag, means it makes the interrupt flag as 0. So that means you are masking the interrupts once you make the IF value as 0. If you are making the IF flag as 1, that means you are enabling the interrupts. So that is the purpose of the interrupt flag. Next important flag is the trap flag. So this decides whether or not the CPU is halted after the execution of a block of instructions. So when this flag is set, the programmer can single step through his program to debug any errors. During software development program, the lengthy code is not executed in one stroke. The longer code is divided into blocks and those modules are executed, and the contents of memory locations or registers are verified to see that the module is working satisfactorily. So this trap flag enables single stepping through the program. So you can execute submodules of the program, then finally you can execute the whole code as one step. So in one stroke. So trap flag, it enables the execution of the program stepwise. So this is useful to debug the program for any errors. So at each time when you execute the program module wise, you can verify the contents of memory registers, whether they are as per the expectation or not. So we have discussed about 3 control flags: the trap flag, the direction flag, and the interrupt flag. Direction flag is to process the array whether in increasing order or descending order. That is the direction flag. Then interrupt flag is whether you can enable or disable the interrupts. And trap flag is to execute the program instruction wise. Next we have the 6 conditional flags. The 6 conditional flags are the carry flag, and followed by the parity flag, then auxiliary carry flag, then sign flag, then overflow flag. These are all the 6 conditional flags. Now let us see what is the carry flag. So the carry flag, it is set when the result of unsigned arithmetic operation is too large to fit into the destination register. So this happens when there is an end carry in an addition operation or there is an end borrow in a subtraction operation. Okay. Now, for example, let us take 8-bit operation like this: 1, 0, 0, 0, then 0, 0, 0, 1. Then let us add this to 1, 0, 0, 1 and 0, 0, 1, 0. So what is this? This is 8, 1, H. And what is this? This is 9, 2, H. So once you do the addition of this, you get here 1, then 1, then 0, 0, 1, 0, 0. So the MSBs are 1. So 1, 1, you get 0 and then 1. So this is the carry. So there is an overflow from the most significant bit. So this activates the carry flag. So the carry flag is set when the result of unsigned arithmetic operation is too large to fit in the destination register and there is a flow bit from the most significant bit. This is for the addition operation. Similarly, if there is a borrow during subtraction operation, then also this flag is activated. Suppose you are subtracting a high magnitude number from the lower magnitude number, obviously you have to borrow. So when there is a borrow also, this carry flag is activated. So that is the importance of the carry flag. Next we have the next let us discuss about the sign flag. So the sign flag is set when the result of an arithmetic or logic operation is negative. So this flag is a copy of the MSB bit. So a value of 1 means negative and 0 means positive. So there is a sign flag. So during the arithmetic and logic operations, if the most significant bit is 1, then this flag is activated. For example, let us see this operation. 5, 5. Let us multiply with AA. Sorry, let us add with AA. Then what you get? What is 5? 5 is 0, 1, 0, 1. There is 5. And another 5, 0, 1, 0, 1. Then A is 1, 0, 1, 0, 1, 0, 1, 0. So if you are adding, what are you going to get? 1, 1, 1, 1. Then 1, 1, 1, 1. So if you are adding these two, you are getting F, F. So please note here that the most significant bit is 1. So when the most significant bit is 1, then this flag is activated. So let us take another example. 0, 1, 1, 1, then 0, 1, 0, 0. So what is this? This is 7, 4, H. Then if you add with 0, 1, 0, 0, 0, 0, 1, 0. What is this? This is 4, 2, H. So once you are adding these two, what are you going to get? You will get 0, 1, 1, 0, 1, 1, 1, 1 is 0, 1. So the most significant bit is 1. So when the most significant bit is 1, then this flag is activated. So this is the sign flag. So during arithmetic and logic operations, this flag is set when the result of operation is negative. So this flag is a copy of the MSB of the result. So a value of 1 means negative, 0 means positive. So this is about the sign flag. Next, let us discuss about the 0 flag. So this flag is set when the result of arithmetic or logic operation is equal to 0. So a value of 1 means that the value or the result is 0, and if the value of 0 means that the result is not 0. So to repeat once again, if the result is 0, then this flag is set, otherwise this flag is not set. For example, if you are deducting 5 from 5, then what are you going to get? 0. So in this case, 0 flag will become 1. Suppose you are deducting 5 from 6. 6 minus 5. So here the result is not 0. So the 0 flag is equal to 0 value. So this is a 0 flag. See, the 0 flag is used in conditional jump instructions, which I am going to give an example after this description of various flags. Now let us discuss about the auxiliary carry flag. And this flag is set when the operation causes a carry from bit 3 to bit 4. That means if there is a carry from the lower nibble to the higher nibble, then this auxiliary carry flag is set. So a value of 1 means that the auxiliary carry flag is 1, and if there is no flow from the lower nibble to the higher nibble, then this flag is 0. Now for example, let us take this 1001, then 1101. Let us take this and let us add with 0001 1000. So what is this? This is 9 8 4 12. See, this is a D. Okay, and this is 1 8. So if you do the addition, you get 1 here, 0 1 1 1 is 0. So this 1 goes here. So 1 1 is 0, and you get triple 1 here, 1 0 1. So you see here, from the lower nibble to the higher nibble, there is a flow, because 1 1 you have added, so you are getting a flow from the lower nibble to the higher nibble, and in that case the auxiliary carry flag is activated. So that is the purpose of auxiliary carry flag. This is mainly used for BCD operations. Now parity flag. This denotes the number of ones in the result. So if the result contains even number of ones, the parity flag is set. Otherwise the parity flag is made as 0. If the result contains odd number of ones, the parity flag is 0. If the result contains even number of ones, then the parity flag is activated. That means it is made as 1. For example, let us take this 0100 0100, that is 44 hexadecimal. Let us add this with 0010 0010. This is 22H. So if you add these two, you get 0110 0110. So this is equal to 66H hexadecimal. And the result contains how many ones here? 1, 2, 3, 4. So the result contains 4 ones. So in this case, the parity flag becomes 1. The parity flag becomes 1 because the result contains even number of ones. So that is an operation of the parity flag. Now let us discuss about the overflow flag. So the overflow flag is set when the result of a signed arithmetic operation is too large to fit in the destination register. So overflow occurs when adding two numbers with the same sign. So a value of 1 is equal to overflow and a value of 0 is not overflow. So if the destination register is not able to accommodate the magnitude, then this overflow takes place. For example, let us do this 7f with 2. What is 7f? 7f is nothing but 1, 2, 7. Okay, and 2 is 2. So if you add these two, what is 7? 0, 1, 1, 1, and f is all ones, and 2 is 0, 0, 0, 0, 0, 0, 1, 0. So if you are adding these two, you get here 1, 1, 1 is 0, 1, 1, 1 is 0, 1, 1, 1 is 0, 1, 1, 1, 1. So you see here, the positive numbers are designated with a sign bit 0. So 127 is positive because the sign bit is 0, and 2 also is positive because the sign bit is 0. And when you are adding these two, the magnitude has come into the sign bit, indicating that this is a negative number. So that means the destination register is not able to accommodate the result. So in such case, the overflow flag becomes 1. So this flag is set when the result of a signed arithmetic operation is too large to fit in the destination register. And this normally occurs when adding two numbers with the same sign. Now let us take another example for overflow case. Suppose you are adding minus 128 with minus 1. So both are negative numbers. And how minus 128 is represented? In 2's complement fashion. Minus 128. First, what is 128? 128 is 1, 0, 0, 0, followed by zeros. So 8, 16, 32. Okay. So this is plus 128. So how it is represented in 2's complement? So this one you have to make it as 0, all ones. Then you add 1. Then you get 1, 0, 0, 0, and all zeros. So this is minus 128. 1, 0, 0, and 0, 0, 0, 0. This is minus 128. And what is 1? 1 is you have like this. This is 1, and minus 1 means you take a complement. Then this becomes 1, 1, 1, 1, 1, 1, 0. Then add 1 because you are taking the 2's complement. So you get all ones. So this is minus 1. So once you are adding this, you get. So 1, 1 is 0, 1. So here you are adding two negative numbers, but you have got 0 in the most significant bit, indicating that this is a positive number by mistake. So in that case, the overflow flag is set. The overflow flag becomes 1. So the overflow flag is activated when the destination register is not able to accommodate the result. And normally this occurs when adding both the positive numbers or negative numbers the when there is a flow of carry into the most significant bit, indicating that it's a it's of a different sign. So when you are adding both positive numbers, you must get a positive number. But if there is a flow of carry into the most significant bit, it wrongly indicates that it is a negative number. In that case, the overflow flag is set. Similarly, when we are adding two negative numbers, the result has to be obviously a negative. But if there is a flow of carry into the most significant bit, it wrongly indicates that it is a positive number. So in that case, the overflow flag is activated. Now let us see a few more examples. So this is, of course, this one we have already discussed just now. Now here, 3 3 with A6. If you are doing the addition, then what is 3 3? 3 3 is 0 0 1 1, then 0 0 1 1, and A6. A is 10, which is nothing but 1 0 1 0, and 6 is 0 1 1 0. So if you are adding 1 1 1 is 0, 1 1 is 0 1 1 1 1 is 0 1 1. So this is the result. So when the most significant bit is 1, obviously the sign flag has to be 1, and the result is not 0, so the 0 flag is not set. So that means the 0 flag is 0, and the result contains how many ones? 1 2 3 4 5. So this contains odd number of ones, so the parity flag is 0, and there is no carry from the most significant bit, so the carry flag is 0. And if you see, there is no flow of carry from the lower nibble to the higher nibble. There is no flow of carry from this is a lower nibble, this is a lower nibble, and this is a higher nibble, and there is no flow of carry from the lower nibble to the higher nibble. So the auxiliary carry flag is 0. So this is how the combination of various flags for the addition of 3 3 with A6. Now let us see the combination of various flags for the addition of FF with 0 1. So this is FF with 0 1. We are doing unsigned arithmetic operation. So F is all ones. So I am adding 1 to that. So what is the result? 1 1 is 0, and 0 0 0 0 0 0 0 1. So here the most significant bit is 0. So the sign flag is 0, and the result is 0. So 0 flag is made 1, and the result contains even number of ones. So the parity flag is 1. So when the result contains even number of ones like 0, 2, 4, 6, then the parity flag is set. In this case, the result contains even number of ones, so parity flag is activated. And there is a flow of carry from the most significant bit. So that is why the carry flag is made as 1. And from the lower nibble to the higher nibble, there is a carry. So the auxiliary carry flag is made as 1. So this is a combination of various flags for the addition of FF with 0 1. Now these flags are used to keep a track on the number of iterations. For example, I'll give you the example of the use of 0 flag for multi-byte addition. Let us say I have an array with 4 numbers, and there is another array with 4 numbers in another location. So these two are added, and the result has to be stored in a different memory location. Let us see the program and how the 0 flag is used for this application. Now move AX 5 0 0 0. Then move DSAX. So that means data segment register, I am initializing with the base address 5000H. Next, move SI 2000H. So that means 200H is moved to the SI register. So what is the physical address I am going to get here? The physical address is 500, and one more 0 is added by the bus interface unit in 8086 microprocessor, and to that the offset address is added 2000. So the 20-bit physical address is 52000. So this is a 20-bit physical address. Similarly, there is another array, and that another array is pointed by the BX register. Move BX 300H. So all these arrays are stored in the data segment with the different offset addresses which are pointed by the SI, BX and DI. Okay, so that means SI is having the offset address 2000. So I am having some 4 elements. So I am planning to do the multi-byte addition for 4 numbers. So the count value I am going to store in the CL register. Move CL 04H. If I am adding 10 numbers, I will say move CL 0AH. If I am adding 15 numbers, I am going to say move CL 0FH. So that is how I should keep the count value in the CL register. Normally the CL register is used to store the count value. Next, move AL SI. So I am moving the contents of memory register pointed by SI to AL. So I am going to move the contents of memory which is pointed by SI to AL. Then add AL BX. So I am going to add the contents of AL register with the contents of memory location which is pointed by BX. Then this has to be stored in the memory location which is pointed by the DI register, destination index register. So move DI AL. So the first element of SI is added with the first element of BX, and the result has been moved to the DI register. Next, what I have to do? I have to add the second elements of the arrays. So for that, I should increment the SI, DI and BX registers. So INC SI, INC DI, increment, similarly BX register. And how many times I have to do? Till the count value becomes 0. So decrement CL. So till the count value becomes 0, I should repeat these operations. So when I do this addition operation for 4 times, then the CL value becomes 0. Say first time the CL is 4. After adding first numbers of the arrays, CL value becomes 3, then 2, then 1, then 0. The moment it becomes 0, you should come out of this loop. So jump, no zero, up. So this is the up. The control should go here. So this is where the zero flag is used. And after that, we end of the program. Okay. So this is one example where the zero flag is used. Similarly, we can use the carry flag also for various applications. And what is this? And please make a note here that move AX 500 and move AX DX. And you cannot write like this, move DS 500H, because moving immediate data to segment registers is prohibited. So always you should move them to AX register. From AX only you can move them to the corresponding segment registers. And what is this type of addressing? This is the immediate addressing. Okay. And what is this type of addressing? Here, if you say move AXSI, it is a register addressing, and it's also called as the direct addressing. But here, I have told move AL with SI in brackets. That means you are moving the contents of SI, you are moving the contents of memory location pointed by SI to AL register. So this is the indirect addressing. So this is how you can do the multi-byte addition. So we have discussed about the various flags of 8086 microprocessor. It has carry flag, parity flag, auxiliary flag, zero flag, sign flag, thief flag, and 3 control flags, direction flag, interrupt flag, and trap flag. The direction flag decides in what order you are processing the array. The interrupt flag either it enables or disables the interrupts, and trap flag you can execute the program instruction wise. And carry flag, if there is a flow of bit from the MSB, yes, this flag is set. The result contains even number of ones, yes, parity flag is set. If there is a flow of carry, or if there is a flow of bit from the lower level to the higher level, auxiliary carry flag is set. If the result is 0, zero flag is set. And sign flag, if the MSB is 1, then the sign flag is set. And overflow, if the destination is not able to accommodate the result in signed operation, then overflow flag is set. So with this, I conclude today's session on the flag register of 8086. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.